Tonight, we're going to talk about something that will completely change how you experience sitting still. Right now, as you're watching this, you're on a journey through space. An extreme one. You're traveling at over 1 million miles per hour. It starts with the Earth spinning beneath you. That spinning Earth is orbiting the Sun. The Sun is flying around the galaxy, and the galaxy itself is racing through the cosmos. All of it stacking together. All of it happening right now. Each layer adding more speed to the last. By the end of tonight, you're going to understand every layer of that invisible motion, see why you can't detect it, and discover where the universe is actually taking us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something simple. From where you are right now, everything feels still. Nothing is moving. Everything is stable, and that matches your direct experience of reality. But your senses are only showing you part of the picture. They're designed to detect relative motion, not absolute motion. They measure movement compared to your immediate surroundings. If everything near you is moving at the same speed, they register nothing, which means you could be traveling at any speed. And as long as everything around you is traveling with you, you'd feel perfectly still. And that's exactly what's happening. The Earth is moving. Fast. Incredibly fast. Let me show you just how fast. The first layer of motion is the one most people know about. Earth is rotating on its axis. It spins like a top, completing one full rotation every 23 hours, 56 minutes, and 4 seconds. We call this a sidereal day. It's slightly shorter than the 24-hour day we use for our clocks because Earth is also moving around the Sun, which adds a few extra minutes to bring the Sun back to the same position in the sky. But let's focus on the rotation itself. Earth's equator has a circumference of about 24,901 miles. That entire distance gets covered in one rotation. So, if you're standing on the equator, you're moving at about 1,040 miles per hour. That's faster than the speed of sound. The speed of sound in air at sea level is about 767 miles per hour. You are moving faster than sound right now if you're near the equator, and you can't feel it. Not even slightly. But here's the thing. Most people don't live at the equator. The speed of Earth's rotation changes depending on your latitude. The farther you are from the equator, the slower you're moving. If you're in New York City at about 40 degrees north latitude, you're moving at roughly 794 miles per hour. If you're in London at about 51 degrees north, you're moving at about 650 miles per hour. If you're standing at the North or South Pole, you're barely moving at all in terms of rotation. You're just slowly spinning in place once every 24 hours. But no matter where you are on Earth, you don't feel this motion. Why not? Because everything around you is moving at the same speed. The air is moving. The ground is moving. The buildings are moving. Your body is moving. There's no relative motion between you and your environment, so there's nothing for your senses to detect. This is the first layer of motion. Earth spinning on its axis. And it's just the beginning. Now, let's talk about Earth's orbit around the Sun. This is the second layer of motion, and it's much faster. Earth orbits the Sun at an average distance of about 93 million miles. We call this distance 1 astronomical unit. The path Earth takes around the Sun is nearly circular, though it's actually a very slight ellipse. The total distance Earth travels in one complete orbit is about 584 million miles, and it completes this orbit in 1 year, 365.25 days. So, how fast is Earth moving? You can calculate it. 584 million miles divided by 365.25 days. That's about 1,600,000 miles per day. Divide that by 24 hours, and you get about 66,600 miles per hour. That's Earth's orbital speed around the Sun. 66,600 miles per hour. To put this in perspective, the fastest jet ever built, the Lockheed SR-71 Blackbird, had a top speed of about 2,193 miles per hour. Earth is moving roughly 30 times faster than that. The fastest spacecraft humans have ever built, the Parker Solar Probe, reached speeds of about 430,000 miles per hour at its closest approach to the Sun. Earth's orbital speed is still slower than that, but not by as much as you might think. We're talking about a planet, a massive ball of rock and metal weighing about 6.6 sextillion tons, and it's hurtling through space at over 66,000 miles per hour. Every single second, Earth moves about 18.5 miles along its orbit. In the time it takes you to read this sentence, Earth has traveled dozens of miles through space. And again, you don't feel any of this, because you're moving with Earth. The atmosphere is moving with Earth. Everything on the surface is moving together. There's no wind from this motion because the air is moving at the same speed as the ground. There's no sensation of speed because everything in your reference frame is moving together. This is a fundamental principle of physics. If you're in a sealed room moving at a constant speed in a straight line, there's no experiment you can do inside that room to determine how fast you're moving. This is the principle of relativity, first understood by Galileo and later refined by Einstein. Motion is relative. You can only detect changes in motion, acceleration. As long as Earth's orbital speed is constant, as long as it's not speeding up or slowing down, you can't feel it. But Earth's orbit isn't perfectly constant. It's slightly elliptical. Earth moves a bit faster when it's closer to the Sun in early January, about 67,600 miles per hour. And it moves a bit slower when it's farther from the Sun in early July, about 65,600 miles per hour. The difference is only about 2,000 miles per hour over the course of 6 months. That's such a gradual change that you'd never feel it. But it's there. So that's the second layer. Earth orbiting the Sun at over 66,000 miles per hour. And we're just getting started. Now let's zoom out further. Earth isn't the only thing moving. The Sun itself is moving. It's orbiting the center of the Milky Way galaxy. Our entire solar system, all the planets, all the asteroids, all the comets, everything is being carried along with the Sun as it moves through the galaxy. The Sun is located about 26,000 light-years from the center of the Milky Way. That's about 153 quadrillion miles. The Sun orbits the galactic center in a nearly circular path, though the exact shape is still being studied. One complete orbit takes about 230 million years. We call this a galactic year, or a cosmic year. The last time the Sun was in the same position in the galaxy, dinosaurs were just beginning to dominate Earth. The next time the Sun completes a full orbit, Earth will be a completely different place, assuming it still exists. But let's focus on the speed. The Sun is moving through the galaxy at about 490,000 miles per hour. That's nearly 500,000 miles per hour. To give you some perspective, That's about 220 times faster than Earth's rotation at the equator. It's about 7 times faster than Earth's orbit around the Sun. The Sun is screaming through space, dragging the entire solar system with it. And you're on Earth, which is inside the solar system, which means you're also moving at 490,000 miles per hour relative to the center of the galaxy. Every second, the Sun moves about 136 miles. In the time it takes you to blink, the Sun has traveled several miles through the galaxy, and you've traveled with it. But again, you don't feel this motion, because everything in the solar system is moving together. Earth is moving with the Sun. The Moon is moving with Earth. The other planets are moving along with us. There's no wind from this motion because the solar system is moving through space that's mostly empty. There's no air resistance at these speeds. The particles of gas and dust between the stars are so sparse that they don't create any noticeable drag. Now, here's something interesting. The Sun isn't moving in a straight line. It's orbiting the galactic center, which means it's constantly changing direction. And that means it's constantly accelerating. Any time you change direction, even if your speed stays the same, you're accelerating. But the curve of the Sun's orbit is so gradual, so enormous, that the acceleration is imperceptible. The centripetal acceleration keeping the Sun in its orbit around the galactic center is absolutely tiny compared to the acceleration you experience just standing on Earth's surface due to gravity. You can't feel it. So that's the third layer. The Sun orbiting the center of the Milky Way at 490,000 miles per hour. And we're still not done. Now, let's talk about the motion of the Milky Way galaxy itself. Because the galaxy isn't standing still either. It's moving through space. And this is where things get complicated, because when you ask how fast the galaxy is moving, you have to ask, moving relative to what? There's no fixed point in the universe. There's no cosmic landmark that's sitting still. Everything is moving. So, when we talk about the motion of the galaxy, we have to pick a reference frame. The most useful reference frame is the cosmic microwave background. The cosmic microwave background, or CMB, is the faint glow of radiation left over from the Big Bang. It fills the entire universe. It's the oldest light we can see, emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. The CMB is almost perfectly uniform in all directions. Almost. There's a very slight temperature difference between one side of the sky and the other. This difference is called a dipole anisotropy. One side of the sky is slightly warmer, and the other side is slightly cooler. The difference is tiny, only about 3.3 millikelvin. But it's measurable, and it tells us something important. It tells us that we're moving relative to the CMB. The side of the sky that's warmer is the direction we're moving toward. The light from that direction is blue shifted, meaning it's compressed because we're moving toward it, which makes it appear slightly warmer. The side of the sky that's cooler is the direction we're moving away from. The light from that direction is red shifted, stretched out because we're moving away from it, which makes it appear slightly cooler. By measuring this temperature difference, scientists can calculate how fast we're moving relative to the CMB. And the answer is about 1,342,000 miles per hour. That's the speed of the Milky Way galaxy through space, relative to the cosmic microwave background. 1.3 million miles per hour. Let that sink in. You are moving at over 1 million miles per hour right now. Not because you're on a spaceship, not because you're in a rocket, But because you're on a planet inside a solar system, inside a galaxy that's moving through the universe at extraordinary speed, every second, the Milky Way moves about 373 miles relative to the CMB. Every minute, it moves over 22,000 miles. Every hour, over 1.3 million miles. In the time it takes you to sleep for 8 hours, the Milky Way has traveled over 10.7 million miles through space. And you were asleep for all of it. You didn't feel a thing. Now, here's where it gets interesting. The Milky Way's motion, relative to the CMB, isn't random. It's not just drifting in some arbitrary direction. The galaxy is being pulled. It's being pulled by gravity. Specifically, it's being pulled toward a region of space called the Great Attractor. The Great Attractor is a gravitational anomaly located about 150 million light-years away in the direction of the constellations Hydra and Centaurus. It's not a single object. It's a massive concentration of mass, possibly a supercluster of galaxies, that's pulling on our galaxy and thousands of other galaxies in our region of space. The Milky Way is falling toward the Great Attractor. Falling might sound wrong, but that's what gravitational motion is. When you orbit something, you're falling toward it, but moving sideways fast enough to keep missing it. When you're being pulled towards something and not orbiting it, you're just falling. The Milky Way is falling toward the Great Attractor at hundreds of miles per second. But even the Great Attractor isn't the end of the story. Beyond the Great Attractor is an even larger structure called the Shapley Supercluster. It's located about 400 million light-years away, and it's pulling on the Great Attractor, which is pulling on us. And beyond that, there are even larger structures. The universe is filled with vast cosmic filaments, walls of galaxies stretching for hundreds of millions of light-years. And all of these structures are moving relative to each other. Some are moving toward each other. Some are moving apart because of the expansion of the universe. So, when you try to calculate the true speed of Earth through space, you have to add up all these layers of motion. But here's the problem. You can't just add them up like simple numbers, because these motions are in different directions. Earth is spinning on its axis, which is tilted relative to the plane of its orbit around the Sun. Earth is orbiting the Sun, which is moving through the galaxy. The galaxy is moving relative to the CMB. All of these motions are happening simultaneously in different directions. To find the total speed, you'd have to use vector addition, treating each motion as a vector with a direction and magnitude. And when you do that, the math gets complicated. But we can get a rough idea. Let's start with the simple case. If you're standing on the equator at local noon, you're rotating with Earth at about 1,040 miles per hour in the direction of Earth's rotation. Earth is orbiting the Sun at 66,600 miles per hour. The Sun is orbiting the galaxy at 490,000 miles per hour. The galaxy is moving relative to the CMB at 1,342,000 miles per hour. If all these motions were in the same direction, which they're not, you'd be moving at over 1.9 million miles per hour. But they're not all in the same direction. Earth's rotation is perpendicular to its orbit around the Sun. The Sun's orbit around the galaxy is at an angle to the plane of the solar system. The galaxy's motion relative to the CMB is in yet another direction. So the actual combined speed is different depending on where you are on Earth and what time of day it is. But the important point is this. You're moving at speeds well over 1 million miles per hour. and you can't feel any of it. Not one bit. So why can't we feel this motion? The answer comes down to a few key principles of physics. First, constant velocity motion is undetectable. If you're moving in a straight line at a constant speed, there's no way to feel that motion. This is why you can't feel Earth's orbital motion around the Sun. Earth is moving at a nearly constant speed in a nearly straight line over short timescales. The curve of the orbit is so gradual that the acceleration is too small to detect. Second, when everything around you is moving at the same speed, there's no relative motion. This is why you can't feel Earth's rotation. The air is rotating with Earth. The ground is rotating. The buildings are rotating. Your body is rotating. There's nothing moving relative to you, so there's nothing to detect. Third, the accelerations involved are incredibly small. The acceleration due to Earth's rotation is only about 0.034 meters per second squared at the equator. Compare that to the acceleration due to gravity, which is 9.8 meters per second squared. You're experiencing an acceleration from gravity that's nearly 300 times stronger than the acceleration from Earth's rotation. The rotation's effect is completely swamped by gravity. Similarly, the centripetal acceleration from Earth's orbit around the Sun is about 0.006 meters per second squared. That's over 1,600 times weaker than gravity. The centripetal acceleration from the Sun's orbit around the galaxy is even smaller, about 2 times 10 to the negative 10th power meters per second squared. That's so small it's effectively zero for any human perception. So, all these motions we've been talking about, all these incredible speeds, they produce accelerations that are far too small for us to detect. We're completely insensitive to them. The only accelerations we can feel are the ones that are large enough to compete with gravity. When you're in a car and it speeds up, you feel pushed back into your seat. That's an acceleration of maybe 2 or 3 meters per second squared, comparable to gravity. That's why you can feel it. When you're in an elevator and it starts moving, you feel lighter or heavier. That's a change in acceleration. That's detectable. But the motion of Earth through space, completely smooth, completely constant, completely undetectable. There's one more reason we can't feel this motion. It's not just about the speed or the acceleration. It's about the medium we're moving through. When you move through air in a car, you feel the wind. The air resistance creates a force on the car, and you feel that force. But when Earth moves through space, it's moving through a near-perfect vacuum. There's almost nothing there. Space isn't completely empty. There are particles of gas, there's dust, there's cosmic radiation. But the density is so incredibly low that the resistance is negligible. At the speeds we're moving, even the thin gas between the stars doesn't create any noticeable drag. So, there's no cosmic wind pushing against Earth. No resistance slowing us down. Nothing to create a sensation of motion. We're moving through a void, and the void doesn't push back. Now, let's talk about something fascinating: the expansion of the universe. Because there's one more layer of motion we haven't discussed, and it's the strangest one. The universe itself is expanding. Space itself is stretching. And this expansion is carrying galaxies apart. This isn't motion through space. This is the expansion of space itself. It's a fundamentally different kind of motion. To understand this, you need to understand what the expansion of the universe really means. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move apart. But the dots aren't moving across the surface of the balloon. The surface itself is stretching, carrying the dots with it. That's what's happening with the universe. Galaxies aren't flying apart through space. The space between them is expanding, pushing them apart. The farther apart two galaxies are, the faster the space between them expands. This is described by Hubble's law. The recession velocity of a galaxy is proportional to its distance from us. The current value of the Hubble constant is about 46 miles per second per megaparsec. A megaparsec is about 3.26 million light-years. So, for every 3.26 million light-years of distance, the recession velocity increases by about 46 miles per second. Let's do some math. A galaxy that's 100 million light-years away is receding from us at about 1,400 miles per second. That's over 5 million miles per hour. A galaxy that's 1 billion light-years away is receding at about 14,000 miles per second. That's over 50 million miles per hour. A galaxy that's 10 billion light-years away is receding at about 140,000 miles per second. That's over 500 million miles per hour. And here's the thing. At a certain distance, the recession velocity exceeds the speed of light. This doesn't violate relativity. Nothing is moving faster than light through space. But space itself can expand faster than light. The boundary where the recession velocity equals the speed of light is the edge of the observable universe. Beyond that boundary, galaxies are receding so fast that their light will never reach us. They're beyond our cosmic horizon. The observable universe has a radius of about 46.5 billion light-years. That's the distance to the farthest objects we can possibly see. Anything beyond that is forever beyond our reach. Their light is being carried away from us faster than it can travel toward us. So, when we talk about the motion of the Milky Way through space, we're talking about motion relative to the cosmic microwave background. But that's just local motion. The expansion of space is happening everywhere. It's happening between the Milky Way and other galaxies. It's even happening inside the Milky Way, though gravity holds the galaxy together and prevents the expansion from tearing it apart. On small scales, gravity dominates. On large scales, expansion dominates. And the expansion is accelerating. This was discovered in the late 1990s by studying distant supernovas. Scientists expected the expansion to be slowing down due to gravity, pulling everything back together. Instead, they found it was speeding up. This was so unexpected that it took years to confirm. But the evidence is solid. The expansion is accelerating, driven by something we call dark energy. We don't know what dark energy is. It might be a property of space itself. It might be a field filling the universe. But whatever it is, it makes up about 68% of the total energy content of the universe. And it's pushing space apart. In the far future, billions of years from now, the acceleration will carry distant galaxies beyond our cosmic horizon. They'll disappear from view. The observable universe will shrink. Eventually, the only galaxies visible will be the ones in our local group, bound together by gravity. Everything else will have been carried away by the expansion of space. But that's billions of years in the future. For now, we can still see a vast universe filled with galaxies. And we're moving through it at incredible speeds. Let's step back and summarize all the layers of motion. First, Earth's rotation, about 1,040 miles per hour at the equator. Second, Earth's orbit around the Sun, about 66,600 miles per hour. Third, the Sun's orbit around the galaxy, about 490,000 miles per hour. Fourth, the galaxy's motion relative to the cosmic microwave background, about 1,342,000 miles per hour. And fifth, the expansion of space itself, carrying distant galaxies away at speeds that increase with distance. All of these motions are happening simultaneously. Right now, as you're sitting still, you're participating in all of them. You're spinning with Earth. You're orbiting the Sun. You're circling the galactic center. You're falling toward the great attractor. You're moving relative to the cosmic microwave background, and the space around you is expanding, all at the same time, and you can't feel any of it. This is one of the most profound realizations in all of science. Motion is relative. There's no absolute reference frame. There's no cosmic grid that marks who's moving and who's standing still. Everything is moving relative to something else. When you say you're sitting still, you mean you're still relative to the ground. But the ground is moving relative to the center of the Earth. The center of the Earth is moving relative to the Sun. The Sun is moving relative to the galaxy. The galaxy is moving relative to the CMB. And the CMB itself is just a reference frame we've chosen because it's useful. It's not more fundamental than any other reference frame. In a very real sense, there's no such thing as absolute motion, only relative motion. And that means the question, how fast am I really moving, doesn't have a single answer. It depends on what you're measuring your motion relative to. Relative to the Earth, you're moving slowly or not at all. Relative to the Sun, you're moving at tens of thousands of miles per hour. Relative to the galaxy, hundreds of thousands. Relative to the CMB, over 1 million. All of these answers are correct. They're just measuring different things. Now let's talk about what all this motion means for space exploration. Because if we're moving this fast, shouldn't that make it easier to travel through space? Can't we just jump off Earth and let the motion carry us somewhere? Unfortunately, no. When you jump off Earth, you're still moving with Earth. You're still orbiting the Sun at 66,000 miles per hour. You're still moving with the solar system at 490,000 miles per hour. All of Earth's motion is your motion too. To travel to another planet, you don't need to account for Earth's absolute motion through space. You only need to account for the relative motion between Earth and your destination. For example, Mars orbits the Sun at about 54,000 miles per hour. Earth orbits at about 66,600 miles per hour. When we send a spacecraft to Mars, we're not fighting against Earth's motion. We're just adjusting the spacecraft's orbit around the Sun so it intersects with Mars's orbit. The spacecraft leaves Earth already moving at 66,600 miles per hour around the Sun. It doesn't have to start from zero. It's already in the reference frame of the solar system. All the rocket needs to do is change the orbit slightly. Speed up a bit to move into a higher, slower orbit that reaches out to Mars's distance. Then, slow down a bit when it arrives at Mars to match Mars's orbital speed. The fact that the Sun is moving through the galaxy at hundreds of thousands of miles per hour is irrelevant. Because Mars is moving at the same speed. They're both in the same reference frame. This is why space missions are planned using the solar system as the reference frame, not the galaxy, and certainly not the cosmic microwave background. Within the solar system, the Sun is essentially stationary. The planets orbit around it. And that's all we need to know to navigate. Navigation in space is all about reference frames. When you're on Earth, looking up at Mars, you see it moving across the sky. But that motion is complicated. Part of it is Mars's actual orbit around the Sun. Part of it is Earth's orbit around the Sun. As Earth moves, our perspective changes, and Mars appears to move relative to the background stars. Sometimes Mars appears to move backward in the sky. This is called retrograde motion. It happens when Earth, moving faster in its inner orbit, overtakes Mars. From our perspective, Mars seems to reverse direction temporarily. Ancient astronomers were puzzled by retrograde motion. They tried to explain it with complicated systems of circles within circles. But once you understand that both Earth and Mars are orbiting the Sun, retrograde motion makes perfect sense. It's just a perspective effect. When planning a mission to Mars, engineers have to account for all of this. They have to predict where Mars will be months in advance. They have to calculate the spacecraft's trajectory so it arrives at the right place at the right time. They have to account for the gravitational influences of Earth, the Sun, Mars, and sometimes other planets. They have to plan course corrections along the way. It's incredibly complex. But it's all done within the solar system reference frame. The galaxy's motion doesn't enter into it. Now, imagine trying to navigate to another star. Suddenly, the galaxy's motion matters. Other stars are moving at different speeds in different directions relative to the Sun. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. That's about 25 trillion miles. Proxima Centauri is moving relative to the Sun at about 14 miles per second. Wait, I said earlier, it was 24 miles per second. Let me clarify. The motion of stars is measured in 3 dimensions. There's radial velocity, the motion toward or away from us. We can measure this using the Doppler shift of the star's light. And there's proper motion, the motion across our line of sight. We can measure this by observing how the star's position changes in the sky over time. Proxima Centauri's radial velocity is about 14 miles per second toward us. Its proper motion is about 2.3 arcseconds per year. That might not sound like much, but at Proxima Centauri's distance, that corresponds to about 12 miles per second across our line of sight. Combining the radial velocity and the tangential velocity, Proxima Centauri is moving at about 24 miles per second relative to the Sun. That's about 86,400 miles per hour. Now, if we sent a spacecraft to Proxima Centauri, we'd have to account for that relative motion. We'd have to aim not at where Proxima Centauri is now, but where it will be when we arrive. At current spacecraft speeds, the journey would take tens of thousands of years. The Voyager 1 spacecraft, the fastest human-made object to leave the solar system, is traveling at about 38,000 miles per hour relative to the Sun. At that speed, it would take over 73,000 years to reach Proxima Centauri. By the time it arrived, Proxima Centauri would have moved. The star travels about 24 miles every second. In 73,000 years, That's about 55 billion miles. Proxima Centauri would be more than twice as far from its current position as it currently is from the Sun. You couldn't aim at where the star is now. You'd have to aim at where it will be. And you'd have to account for the Sun's motion too. The Sun is also moving relative to nearby stars. From Proxima Centauri's perspective, the Sun is moving. So, your spacecraft would need to account for both the Sun's motion and Proxima Centauri's motion. It's like trying to hit a moving target while you're also moving. Not in a straight line, but in curves determined by the gravitational fields of every object you pass. The math gets complicated fast. This is why interstellar navigation is so challenging. It's not just the distance. It's the fact that everything is moving in different directions at different speeds. And you can't stop to ask for directions. Once you launch, you're committed to your trajectory. You can make small course corrections, but you have limited fuel. You have to get it right from the start. We'd need to go much faster to make interstellar travel practical. Breakthrough Starshot, a proposed mission, aims to send tiny light sail probes to Proxima Centauri at 20% of the speed of light. That's about 134 million miles per hour. At that speed, the journey would take about 20 years. But even at those incredible speeds, we'd still have to account for the relative motion of the stars. Proxima Centauri would move about 10 billion miles during the 20-year journey. That's about the distance from the Sun to Neptune. You'd have to aim that far ahead of where the star appears to be now. And you'd have to account for relativistic effects. At 20% of light speed, time dilation becomes noticeable. Time on the probe would run about 2% slower than time on Earth. The journey that takes 20 years from Earth's perspective would take about 19.6 years from the probe's perspective. Not a huge difference, but measurable. And if we ever figure out how to go faster, the relativistic effects become more pronounced. At 50% of light speed, time dilation is about 13%. At 90%, it's over 50%. At 99%, time on the spacecraft runs 7 times slower. You'd also have to deal with length contraction. At high speeds, distances in the direction of travel appear shorter. At 99% of light speed, the 4.24 light-year distance to Proxima Centauri would appear to be only about 0.6 light-years from the spacecraft's perspective. This isn't an illusion. It's a real physical effect. Space itself is contracted in the direction of motion. From Earth's perspective, the journey takes 4.3 years at 99% of light speed. From the spacecraft's perspective, the journey takes about 7 months because both time is running slower and the distance is shorter. These are real effects, confirmed by countless experiments. They're consequences of traveling at speeds close to the speed of light, and they make interstellar navigation even more complicated. You can't just use Newtonian physics. You have to use Einstein's special relativity. You have to account for time dilation, length contraction, and the relativistic addition of velocities. Interstellar space isn't empty. It's filled with the motions of stars, each following its own path through the galaxy. Each star has its own velocity relative to the galactic center. Each star has its own velocity relative to nearby stars. And navigating through that requires understanding not just our motion, but the motion of every object we want to reach. It requires precise measurements of stellar positions and velocities. It requires powerful computers to calculate trajectories years or decades in advance. It requires technology we don't yet have to propel spacecraft to the necessary speeds. But it's possible in principle. The laws of physics allow it. We're just not there yet, technologically. Maybe in 100 years. Maybe in 1,000. But someday, if humanity survives and continues to develop, we'll figure it out. We'll send probes to other stars. We'll map the motions of nearby stellar systems. We'll navigate the galaxy. And all of it will depend on understanding motion. Understanding that nothing in the universe is still. Everything is moving. And to get anywhere, you have to account for all that motion. There's another consequence of all this motion. It affects how we see the universe. Light from distant objects is affected by motion in several ways. First, there's the Doppler effect. If an object is moving toward you, the light waves get compressed. The wavelength gets shorter. This is called blue shift because the light shifts toward the blue end of the spectrum. If an object is moving away from you, the light waves get stretched. The wavelength gets longer. This is called redshift because the light shifts toward the red end of the spectrum. We use this effect to measure the speeds of stars and galaxies. By looking at the spectrum of light from a star, we can see how much the light has been shifted. And that tells us how fast the star is moving toward or away from us. Most galaxies are redshifted because the universe is expanding. They're moving away from us. The farther away they are, the faster they're receding. This is Hubble's law, the relationship between distance and recession velocity. But a few nearby galaxies, like Andromeda, are blue shifted because they're moving toward us. Their light waves are compressed, shifted toward shorter wavelengths. Andromeda, also known as M31, is the nearest large galaxy to the Milky Way. It's about 2.5 million light-years away. That's about 15 quintillion miles. Andromeda is on a collision course with the Milky Way. It's approaching at about 68 miles per second. That's about 244,800 miles per hour. Now, 68 miles per second might not sound that fast compared to the other speeds we've been talking about. Earth orbits the Sun at 18.5 miles per second. The Sun orbits the galaxy at about 136 miles per second. But here's the difference. Andromeda is moving directly toward us. It's not orbiting us. There's no sideways motion to make it miss. It's on a direct collision course. In about 4 billion years, give or take a few hundred million, Andromeda and the Milky Way will collide. This sounds violent, catastrophic, apocalyptic. Two galaxies smashing together at hundreds of thousands of miles per hour. But it's actually a slow-motion event on human timescales. 4 billion years is an incredibly long time. 4 billion years ago, Earth had just barely cooled enough to have liquid water on its surface. Life was just beginning to emerge. Simple, single-celled organisms in the oceans. Multicellular life wouldn't exist for another 3 billion years. Humans have existed for only about 300,000 years. 4 billion years is over 13,000 times longer than all of human history. So, the collision is unimaginably far in the future. But it will happen. The evidence is clear. Andromeda's blue shift shows it's approaching. The sideways motion, measured by observing how Andromeda's position shifts against background galaxies, shows it's not going to miss us. The trajectory calculations show a direct collision. Actually, there might be a near miss on the first pass. The two galaxies might swing past each other, gravitationally distorting each other's structures. Then, they'd swing back around for a second collision. And then, a third. Eventually, they'd merge completely. Computer simulations have modeled this process. The animations are stunning. Two massive spiral galaxies approach each other. Their spiral arms start to distort as they get closer. Tidal forces, the same forces that create ocean tides on Earth, pull and stretch the galaxies. Long streamers of stars get pulled out into space. The galaxies pass through each other. Stars from one galaxy intermingle with stars from the other. But here's the thing. The stars are so far apart that very few will actually collide. The Milky Way contains about 200 billion stars. Andromeda contains about 1 trillion stars. That's a lot of stars. But galaxies are mostly empty space. The average distance between stars in our neighborhood of the Milky Way is about 4 light-years. That's about 25 trillion miles. A star is typically about 1 million miles across. That's a 1 million-mile object in a region of space 25 trillion miles across. It's like having a grape in a region the size of North America. When two galaxies collide, the stars mostly just pass by each other. The probability of any two stars actually colliding is incredibly small. Essentially, 0. So, if the Sun and Earth still exist in 4 billion years, which is questionable for other reasons, they'll probably survive the collision unscathed. The night sky will look dramatically different, though. As Andromeda approaches, it will grow larger in the sky. Currently, Andromeda appears about 6 times wider than the full moon. But it's so faint, you need dark skies to see it with the naked eye. As it gets closer, it will get brighter and larger. Eventually, it will dominate the night sky. A massive glowing band stretching across half the visible sky. During the collision, the sky will be filled with stars from both galaxies. New stars will be forming at an incredible rate as gas clouds from the two galaxies collide. Gas doesn't pass through gas the way stars pass through stars. When gas clouds collide, they compress. Compressed gas can collapse under its own gravity and form new stars. The collision will trigger a massive burst of star formation. Millions of new stars will be born. The night sky will be ablaze with bright young stars and glowing gas clouds. It will be spectacular. But there's also danger. The collision will disrupt the galaxy's structures. The spiral arms will be torn apart. Stars will be flung out into intergalactic space. The Sun might be one of them. Computer simulations suggest about 10 to 20% of stars will be ejected from the merged galaxy. If the Sun is ejected, it will end up in intergalactic space. The night sky from Earth would go dark. No Milky Way. No Andromeda. Just the Sun, the planets, and an empty black sky. The nearest stars would be millions of light-years away, too far to see with the naked eye. It would be lonely. But the Sun and Earth would continue on, orbiting through empty space. Or the Sun might stay within the merged galaxy. Either way, the merger will eventually produce a new galaxy. The two spiral galaxies will merge into a single large elliptical galaxy. Elliptical galaxies are more blob-shaped than spiral galaxies. They don't have the distinctive spiral arms. They're made mostly of older stars. Star formation has mostly stopped. astronomers have already given this future galaxy a name: Milkomeda, a combination of Milky Way and Andromeda. Milkomeda will be much larger than either galaxy alone. It will contain about 1.2 trillion stars, and it will continue moving through space, pulled by the gravity of distant structures. Actually, the collision might not happen exactly as I've described. There's another factor: the expansion of the universe. Space is expanding, pushing galaxies apart. So why aren't the Milky Way and Andromeda being pushed apart? Because they're gravitationally bound. They're close enough that their mutual gravity is stronger than the expansion of space between them. They're part of the same local group of galaxies. About 50 galaxies total, most of them small. The local group is held together by gravity. The expansion of space is happening, but it's not strong enough to overcome gravity on this scale. On larger scales, expansion dominates. Galaxies outside our local group are being carried away, but within the local group, gravity wins. That's why Andromeda is approaching. That's why the collision will happen, unless something unexpected changes the dynamics. But current evidence suggests the collision will happen as predicted. There's also another effect called aberration. Because we're moving through space, the direction we see starlight coming from is slightly different than the true direction to the star. This is similar to how rain appears to come at an angle when you're driving, even if it's falling straight down. If you're standing still and rain is falling straight down, it hits you from directly above. You'd hold your umbrella directly over your head. But if you start walking forward, the rain appears to come at an angle from ahead of you. Not because the rain changed direction, but because you're moving into it. You'd tilt your umbrella forward to stay dry. The faster you walk, the more you have to tilt the umbrella. The same thing happens with starlight. Stars are so far away that their light rays are effectively parallel by the time they reach us. The light is coming straight at us from the star's direction. But because Earth is moving through space, we're moving into the light. From our perspective, the light appears to come from slightly ahead of Earth's motion. This effect is called stellar aberration, and it was first observed by James Bradley in 1728. Bradley was trying to measure stellar parallax, the apparent shift in a star's position due to Earth's motion around the Sun. Parallax is a geometric effect. As Earth orbits the Sun, our viewing angle to nearby stars changes slightly. Nearby stars appear to shift back and forth against the background of more distant stars. The amount of shift depends on the star's distance. The closer the star, the larger the parallax. Bradley was observing a star called Gamma Draconis, looking for this parallax shift, but what he found didn't match the expected parallax pattern. The star's position shifted, but in the wrong direction and with the wrong timing. After careful analysis, Bradley realized he was seeing a different effect. The apparent position of the star was shifting because Earth's velocity was changing direction as it orbited the Sun. When Earth is moving toward the star appears slightly ahead of its true position. When Earth is moving away, the star appears slightly behind. When Earth is moving perpendicular to the star's direction, the shift is at its maximum. The shift changes throughout the year as Earth's velocity vector rotates. This is aberration. Bradley measured the aberration angle to be about 20.5 arcseconds. That's less than 0.006 degrees. Tiny, but measurable with 18th century telescopes. From the aberration angle and Earth's orbital speed, Bradley was able to calculate the speed of light. He didn't have an independent measurement of Earth's orbital speed at the time, but later measurements confirmed his reasoning. The aberration angle depends on the ratio of Earth's orbital speed to the speed of light. Earth orbits at about 18.5 miles per second. Light travels at about 186,000 miles per second. The ratio is about 1 to 10,000. The aberration angle is Earth's speed divided by the speed of light, which gives about 20 arc-seconds. This was one of the first accurate measurements of the speed of light, and it provided direct evidence that Earth is moving through space. Before Bradley's discovery, the heliocentric model proposed by Copernicus was still debated. Some people believed the Sun orbited Earth, not the other way around. Bradley's observation of stellar aberration showed that Earth must be moving. There was no other way to explain the effect. If Earth was stationary and the Sun orbited around it, there would be no aberration. The stars would appear in fixed positions throughout the year. But they don't. Their positions shift in a pattern that exactly matches Earth's orbital motion. It was one of the first direct proofs that the Copernican model of the solar system was correct. Stellar aberration affects every star in the sky. The exact amount and direction of the shift depends on the star's position and Earth's current velocity. Stars near the ecliptic, the plane of Earth's orbit, show the maximum aberration. Stars near the ecliptic poles show less. Modern telescopes have to correct for aberration to accurately measure stellar positions. The Hubble Space Telescope, for example, has to account for aberration when targeting distant galaxies. Without correction, the telescope would point in slightly the wrong direction. The error is only about 20 arc-seconds, but at Hubble's resolution, that's significant. Aberration also affects the Gaia spacecraft, a European Space Agency mission that's mapping the positions of over 1 billion stars in the Milky Way. Gaia is measuring stellar positions with incredible precision, down to micro-arc-seconds. That's a millionth of an arc-second. At that precision, Gaia has to account not just for Earth's orbital motion, but for the Sun's motion through the galaxy. The Sun is moving at about 155 miles per second relative to nearby stars. That's about 560,000 miles per hour. This creates an aberration effect larger than the one from Earth's orbit. About twice as large, actually. Gaia has to correct for this to get accurate stellar positions. The spacecraft's observations are affected by its own motion through space. By carefully measuring and correcting for aberration, Gaia can determine the true positions of stars. And by measuring how those positions change over time, Gaia can determine the stars' motions, their velocities through the galaxy. This is creating the most detailed map ever made of the Milky Way's structure and motion. We're learning how the galaxy rotates, how stars move through it, how the spiral arms form and dissolve over time, all because we can measure aberration with incredible precision. Aberration is a direct consequence of motion. It's evidence that we're moving through space. And by measuring it carefully, we can determine exactly how we're moving. Let's talk about time, because motion affects time. According to Einstein's theory of special relativity, time runs slower for objects that are moving relative to you. This is called time dilation. The faster something moves, the more time slows down for it. But the effect is only noticeable at speeds close to the speed of light. At the speeds we're talking about in everyday life, the time dilation is incredibly small. Let's do the calculation for Earth's motion. Earth is moving around the Sun at about 66,600 miles per hour. That sounds fast, but let's convert it to a more useful unit. 66,600 miles per hour is about 18.5 miles per second. The speed of light is about 186,000 miles per second. So, Earth's orbital speed is about 0.01% of the speed of light, 1/10,000th of light speed. At that speed, the time dilation factor is incredibly close to 1. If you calculate it precisely, time on Earth runs about 0.000000005 slower than it would in a stationary reference frame. That's 5 parts in 10 trillion. If you were on Earth for 1 year, and someone was in a stationary reference frame watching Earth orbit the Sun, they would measure your year as being shorter by about 0.0000005 seconds. That's 5 nanoseconds per year. 5 billionths of a second. You'd never notice it in a human lifetime. You'd never notice it in a million lifetimes. It's completely negligible. Even the Sun's motion through the galaxy at 490,000 miles per hour is still small compared to the speed of light. 490,000 miles per hour is about 136 miles per second. That's about 0.07% of the speed of light. 7 parts in 10,000. The time dilation at that speed is still negligible. Time would run slower by about 0.000003. 3 parts in 100 million. If you spent a year moving at the Sun's speed through the galaxy, you'd age about 1/millionth of a second less than someone in a stationary frame. Still completely unnoticeable. You'd have to be moving at a significant fraction of the speed of light, say 10% or more, before time dilation becomes noticeable. At 10% of light speed, time dilation is about 0.5%. Time runs about 99.5% as fast as normal. If you traveled for 1 year at 10% of light speed, you'd age about 2 days less than someone who stayed stationary. Measurable, but not dramatic. At 50% of light speed, time dilation becomes more significant. Time runs about 87% as fast. A year of travel would age you about 7 weeks less than someone stationary. At 90% of light speed, the effects become dramatic. Time runs about 44% as fast. A year of travel would age you only about 5.3 months, while 815.8 months pass for someone stationary. No, wait, let me recalculate that. At 90% of light speed, the time dilation factor is 1 divided by the square root of 1 minus 0.9 squared. That's 1 divided by the square root of 0.19. That's 1 divided by about 0.436. That's about 2.3. So, time runs about 2.3 times slower. If you travel for 1 year from your perspective, about 2.3 years pass for someone stationary. At 99% of the speed of light, time runs about 7 times slower for you than for someone at rest. If you travel for 1 year from your perspective, about 7 years pass on Earth. At 99.9%, time runs about 22 times slower. 1 year for you equals 22 years on Earth. At 99.99%, time runs about 70 times slower. 1 year for you equals 70 years on Earth. This is how time dilation could theoretically allow interstellar travel within a human lifetime. If you could build a spacecraft that travels at 99.9% of the speed of light, you could reach a star 10 light-years away in just over 10 years from Earth's perspective. But from your perspective on the ship, the journey would only take about 5 months. Time would be running 22 times slower for you. You could travel to distant stars and return within your lifetime, from your perspective, but everyone you knew on Earth would be much older or gone. You'd be traveling into Earth's future. This isn't science fiction. This is what Einstein's equations predict. And it's been confirmed by experiments with particles in accelerators. Muons are unstable particles created when cosmic rays hit the atmosphere about 10 miles up. They travel downward at close to the speed of light. But muons decay with a half-life of about 2.2 microseconds. In that time, even traveling at light speed, a muon should only travel about 2,000 feet before decaying. That's less than half a mile. Muons created 10 miles up shouldn't reach the ground. But they do. We detect them at sea level all the time. How? Time dilation. The muons travel at about 99.9% of light speed. At that speed, time runs about 22 times slower for them. From our perspective, their half-life extends to about 49 microseconds instead of 2.2. Long enough to travel 10 miles and reach the ground before decaying. From the muon's perspective, time runs normally. It experiences its normal 2.2 microsecond half-life. But from its perspective, the distance to the ground is contracted. The 10-mile distance appears to be less than half a mile. So, it can cover the distance in its short lifetime. Both perspectives are correct. Both explanations are equally valid. They're different ways of describing the same relativistic effect. This has been verified countless times in particle accelerators. Particles traveling at 99.99% of light speed, or faster, live much longer than their stationary counterparts before decaying. The effect is exactly what Einstein's equations predict. Time dilation is real. So, in principle, the motion we've been talking about, the million-mile-per-hour speed of the Milky Way through space, could be used for time dilation effects. If you could somehow leave the Milky Way's reference frame and then return, the change in velocity would cause time dilation. But the effect would be so small you'd never measure it. At 1 million miles per hour, we're still only talking about 0.15% of the speed of light. The time dilation would be about 2 parts in a million. If you traveled for a year at that speed, you'd age about 1 minute less than someone stationary. Measurable with atomic clocks, but not noticeable to a human. You'd need to travel at relativistic speeds, speeds close to light speed, for time dilation to matter in a practical sense. And we're nowhere close to building spacecraft that can do that. The fastest spacecraft we've built, the Parker Solar Probe, reaches about 0.06% of light speed. At that speed, time dilation is about 2 parts in 10 million. Completely negligible. To get significant time dilation, we'd need to accelerate to at least 10 or 20% of light speed. That requires enormous amounts of energy. The kinetic energy of an object increases with the square of its velocity. Double the speed, quadruple the energy. But as you approach light speed, things get even worse. Einstein's relativity says that as you approach light speed, your mass effectively increases. The faster you go, the more massive you become from an outside perspective. And the more massive you are, the more energy it takes to accelerate you further. At 99.9% of light speed, your effective mass is 22 times your rest mass. It takes 22 times as much energy to accelerate you further. As you get closer and closer to light speed, your effective mass approaches infinity. The energy required to reach light speed would be infinite. That's why nothing with mass can ever reach light speed. Only massless particles like photons can travel at light speed. Everything else is limited to slower speeds. This is one of the fundamental limits imposed by relativity. No matter how powerful your rocket, you can never reach light speed. You can get arbitrarily close, 99%, 99.9%, 99.99%. But you can never quite get there. And the closer you get, the more energy it takes to go faster. For a spacecraft weighing 1 ton to reach 99% of light speed would require energy equivalent to about 100 million tons of matter-antimatter fuel. That assumes perfect conversion of mass to energy, which we don't know how to do. With current rocket technology using chemical fuel, it's impossible. Even with nuclear fusion, it's barely conceivable. We'd need some breakthrough in physics or engineering. Maybe antimatter propulsion. Maybe fusion ramjets that scoop up interstellar hydrogen as fuel. Maybe something we haven't thought of yet. Now let's talk about the practical implications of all this motion. Does it affect our daily lives in any way? Actually, yes, in small but important ways. First, there's GPS. The global positioning system relies on a network of satellites orbiting Earth. There are 31 GPS satellites in orbit at any given time. They orbit at an altitude of about 12,550 miles above Earth's surface. At that altitude, they complete one orbit every 12 hours. These satellites are moving at about 8,650 miles per hour relative to Earth's surface. At that speed, time dilation is small but measurable. According to Einstein's theory of special relativity, moving clocks run slower. The satellite's clocks run slightly slower than clocks on the ground. The effect is about 7 microseconds per day. That doesn't sound like much, but it matters. But there's another effect working in the opposite direction. The satellites are in a weaker gravitational field than we are on the surface. According to general relativity, Einstein's theory of gravity, time runs faster in weaker gravitational fields. This might seem counterintuitive, but it's been proven countless times. Clocks at higher altitudes run faster than clocks at sea level. The difference is tiny, but it's real. For GPS satellites orbiting 12,000 miles up, this effect makes their clocks run about 45 microseconds per day, faster than clocks on Earth's surface. So, you have two competing effects. Special relativity makes the clocks run 7 microseconds per day slower. General relativity makes the clocks run 45 microseconds per day faster. The two effects partially cancel out, but not completely. The net result is that the satellite's clocks gain about 38 microseconds per day compared to clocks on Earth. 38 microseconds might not sound like much. It's 38 millionths of a second. But GPS works by timing how long it takes radio signals to travel from the satellites to your receiver. Radio signals travel at the speed of light, about 186,282 miles per second. In 38 microseconds, light travels about 7 miles. So, if the GPS satellites didn't correct for these relativistic time dilation effects, your position would be off by about 7 miles, and that error would accumulate. After 1 day, the error would be 7 miles. After 2 days, 14 miles. Within a week, GPS would be completely useless for navigation. Your phone would think you're in a different city. Your car's navigation system would give you directions to nowhere. So, GPS satellites have to constantly correct for relativistic effects caused by motion and gravity. The satellite's clocks are programmed to run slightly slower than they naturally would, compensating for the relativistic effects. Every time you use GPS to navigate, you're relying on corrections for the effects of motion through space. You're relying on Einstein's theories of relativity. Without them, GPS simply wouldn't work. This is one of the most practical applications of relativity in everyday life. Most people think of relativity as abstract physics, something that only matters for black holes and the Big Bang. But relativity matters every time you check your phone's map. Every time you use turn-by-turn navigation. Every time a package gets delivered to your house using GPS coordinates. All of that relies on understanding how motion through space affects the passage of time. The engineers who designed GPS had to account for the fact that Earth is rotating at over 1,000 miles per hour at the equator. They had to account for the fact that the satellites are moving at over 8,000 miles per hour. They had to account for the curvature of space-time caused by Earth's mass. All of this motion, all of these relativistic effects, they're baked into the system. And it works. GPS is accurate to within about 16 feet under normal conditions. Some specialized systems can achieve accuracy down to a few inches, all because we understand how motion affects time. Second, there's cosmic radiation. Earth is constantly being bombarded by high-energy particles from space. These cosmic rays are mostly protons, traveling at close to the speed of light. Some are traveling at 99.99% of light speed or faster. They come from supernova explosions, neutron stars, black holes, and other violent events in the galaxy. Some come from events in other galaxies. Some might even come from the Big Bang itself. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles. A single high-energy cosmic ray can create thousands or millions of secondary particles. These particles rain down on the surface constantly. About 10,000 cosmic ray particles hit every square meter of Earth's surface every minute. You're being hit by cosmic rays right now. Dozens of them are passing through your body every second. Most of them pass through you harmlessly. Your body is mostly empty space at the atomic level, so most particles just zip right through. But some can damage DNA and potentially cause cancer. The risk is small at ground level because Earth has two forms of protection. First, Earth's magnetic field deflects many cosmic rays. Charged particles spiral along magnetic field lines. Earth's magnetic field funnels cosmic rays toward the poles. That's why the aurora borealis and aurora australis happen near the Arctic and Antarctic. Those glowing lights are caused by cosmic rays hitting the upper atmosphere. Second, the atmosphere absorbs many more cosmic rays. The atmosphere is thick. At sea level, there's about 10 tons of air above every square meter. Cosmic rays collide with air molecules. The collisions create showers of particles that gradually lose energy as they cascade down through the atmosphere. By the time they reach the ground, most of the energy has been absorbed, but some still get through. If you fly in an airplane, you're exposed to higher levels of cosmic radiation. At cruising altitude, about 35,000 feet, the atmosphere above you is much thinner. Only about 3 tons of air per square meter instead of 10. Cosmic radiation at that altitude is about 100 times higher than at sea level. Pilots and flight attendants, who spend thousands of hours in the air, receive measurable radiation doses. It's still not dangerous for occasional travelers, but it's something that airlines and aviation authorities monitor. Astronauts in space are exposed to much higher levels of cosmic radiation. The International Space Station orbits at about 250 miles up. There's almost no atmosphere at that altitude, and the magnetic field is weaker. Astronauts on the ISS receive radiation doses about 150 times higher than people on the ground. During a 6-month stay on the ISS, an astronaut receives about the same radiation dose as getting a full-body CT scan every 5 or 6 days. It's manageable for short missions. But for longer missions, radiation becomes a serious concern. Mars is even worse. Mars has no global magnetic field. It has almost no atmosphere. The atmospheric pressure on Mars is less than 1% of Earth's. Astronauts on Mars would be exposed to the full force of cosmic radiation. A trip to Mars takes about 6 to 9 months each way. During that time, astronauts would be traveling through interplanetary space with no protection except their spacecraft's hull. The radiation dose for a round trip to Mars would be significant, enough to noticeably increase cancer risk. And the faster we travel through space, the more cosmic rays we encounter. If we ever send humans to Mars or beyond, we'll have to shield them from cosmic radiation. We could build spacecraft with thick walls made of water or plastic. Materials with lots of hydrogen atoms are good at stopping cosmic rays. We could use magnetic fields to deflect particles, creating an artificial magnetosphere around the spacecraft. We could limit mission duration to reduce total exposure. Or we could accept the risk and send astronauts anyway, knowing they're taking a chance. This is one of the major challenges of long-duration space travel, not the lack of air or water or food. Those are engineering problems with known solutions. Cosmic radiation is a physics problem. It's a consequence of motion through space. As long as we're traveling through the galaxy at hundreds of thousands of miles per hour, we're going to encounter high-energy particles, and there's no way to completely avoid them. Third, there's the cosmic microwave background. Because we're moving relative to the CMB at over 1 million miles per hour, the CMB appears slightly warmer in the direction we're moving and slightly cooler in the opposite direction. This dipole, anisotropy, is how we measure our motion through space. But it also means that the universe looks slightly different depending on which direction you're looking. This doesn't affect daily life, but it's an important consideration for cosmology. When scientists study the CMB to learn about the early universe, they have to correct for our motion through space. They have to subtract out the dipole anisotropy to see the underlying structure. And fourth, there's the expansion of space. The expansion doesn't affect us locally because gravity holds the solar system together. But on very large scales, it changes the universe. Galaxies that are billions of light years away are receding from us. Their light is redshifted. And because of the expansion, we can see galaxies that are now beyond our cosmic horizon. The light we're seeing from them was emitted billions of years ago when they were closer. But the expansion has carried them beyond the edge of the observable universe. We're seeing them as they were, not as they are. and we'll never see them as they are now, because their current light will never reach us. The expansion is constantly changing the observable universe. New light from distant galaxies is arriving. Old galaxies are disappearing beyond the horizon. The universe we see is not the universe as it is, but the universe as it was at different times in the past. And all of this is a consequence of motion. Motion through space. Motion of space itself. Let's talk about something philosophical. What does all this motion mean for our place in the universe? For most of human history, we thought we were at the center. The Earth was stationary. Everything else moved around us. The sun, moon, and stars revolved around Earth. We were special, important, the point around which the cosmos turned. This made sense based on observation. When you stand on the ground and look up, it really does look like the sky is rotating around you. This geocentric view lasted for thousands of years. But then Copernicus showed that Earth orbits the Sun. Published in 1543, his model placed the Sun at the center. Earth became just another planet. This was revolutionary. The Catholic Church opposed the idea for centuries, but the evidence kept mounting. Then, we discovered that the Sun is just one star among billions in the Milky Way. We weren't at the center of the galaxy. We're located out in the suburbs, about halfway between the center and the edge. Nothing special about our location. Then, we discovered that the Milky Way is just one galaxy among trillions in the universe. We weren't at the center of the universe. In fact, the universe doesn't have a center. The Big Bang happened everywhere, simultaneously. Every point in space is equally valid as the center of expansion. And now we know that we're moving through space at over 1 million miles per hour, being pulled by gravity toward distant structures we can barely see. We're not at the center of anything. We're not stationary. We're just one small planet in one small solar system, in one galaxy among trillions, all of which are moving through an expanding universe. This is sometimes called the Copernican principle. The idea that we're not special, that there's nothing unique about our location or our motion. We're typical, average, unremarkable. And in a way, that's humbling. It puts us in our place. It reminds us that the universe doesn't revolve around us. Literally. We're not the main characters in some cosmic drama. We're just observers, trying to understand what's happening. Tiny beings on a tiny planet, looking up at a vast universe and wondering what it all means. But there's another way to look at it. Yes, we're small. Yes, we're moving through space at incredible speeds. Yes, we're not at the center of anything. But we're also the only beings we know of who can understand this. We're the only ones who can measure the cosmic microwave background and calculate our motion through space. We're the only ones who can build telescopes and see galaxies billions of light years away. We're the only ones who can figure out that we're moving at over 1 million miles per hour and explain why we can't feel it. We're the only ones who can contemplate our place in the cosmos. That's remarkable. That's extraordinary. Out of all the planets in all the galaxies, Earth is the one that produced a species capable of understanding the universe, capable of asking questions about motion and time and space, capable of figuring out the answers. We might not be at the center. We might not be stationary. But we're conscious. We're curious. We're capable of wonder. And that makes us special in a different way. Not special because of where we are, but special because of what we can do. We can think. We can question. We can explore. And we can understand. We're made of atoms, forged in the hearts of ancient stars. We're the universe's way of knowing itself. Through us, unconscious matter has become conscious. That's profound. Now, let's come back to the question we started with. How fast are we really moving through space? And the answer is, it depends on what you mean by really. If you mean relative to the Earth's surface, you're barely moving. Maybe a few miles per hour if you're walking. If you mean relative to the center of the Earth, you're moving at up to 1,040 miles per hour due to Earth's rotation. If you mean relative to the Sun, you're moving at about 66,600 miles per hour. If you mean relative to the center of the galaxy, you're moving at about 490,000 miles per hour. If you mean relative to the cosmic microwave background, you're moving at about 1,342,000 miles per hour. All of these answers are correct. They're just measuring different things. There's no single true speed. Motion is always relative. And that's one of the deepest insights in all of physics. There's no absolute reference frame, no cosmic grid, no universal clock, just different perspectives, all equally valid. When Einstein developed his theory of relativity, this was one of his key insights. Motion is relative. Time is relative. Even space itself is relative. What's absolute is the speed of light and the laws of physics. Those are the same for everyone, no matter how fast they're moving. But speed itself? That depends on who's measuring. So, the next time someone asks you how fast you're moving, you can give them a range. Anywhere from 0 miles per hour to over 1 million miles per hour. And you'd be right either way. It just depends on the reference frame. Let's talk about the future. What will happen to all this motion as the universe continues to evolve? First, Earth's rotation is slowing down. The moon's gravity creates tidal bulges on Earth. Here's how it works. The moon's gravity pulls on Earth. It pulls strongest on the side closest to the moon. It pulls less strongly on Earth's center. And it pulls even less strongly on the far side. This difference in gravitational pull, called a tidal force, stretches Earth slightly. The solid Earth deforms a bit, but not much. The oceans deform much more. Water on the side of Earth facing the moon gets pulled toward the moon, creating a bulge. Water on the far side also bulges outward, because it's being pulled less strongly than Earth's center. So, Earth has two tidal bulges, one facing the moon and one on the opposite side. As Earth rotates, different parts of the planet pass through these bulges. When you're in a bulge, the ocean is higher. That's high tide. When you're between the bulges, the ocean is lower. That's low tide. Most coastal areas experience 2 high tides and 2 low tides every day as Earth rotates through the 2 bulges. But here's the key part. Earth's rotation is faster than the moon's orbit. Earth rotates once every 24 hours. The moon orbits Earth once every 27.3 days. So, Earth is trying to drag the tidal bulges along with it as it rotates. But the moon's gravity is trying to keep the bulges aligned with the moon. The result is friction. The tidal bulges are slightly ahead of the line between Earth and the moon. This creates a torque, a twisting force that slows Earth's rotation. It's like a brake. The friction between the moving water and the ocean floor dissipates energy. That energy comes from Earth's rotation. As Earth loses rotational energy, it spins more slowly. The effect is small. Earth's day is getting longer by about 1.7 milliseconds per century. That's 1.7 thousandths of a second every 100 years. You'd never notice it in a human lifetime. But over geological time, it adds up. About 600 million years ago, a day on Earth was only about 21.5 hours long. Back when the first complex multicellular life was evolving in the oceans, the Earth was spinning faster. A year still had about 365 days, but each day was shorter. So, there were more days in a year. We know this from studying growth rings in ancient corals. Corals lay down daily growth rings, like trees do. By counting the rings between seasonal markers, paleontologists can determine how many days were in a year hundreds of millions of years ago. The data confirms that days were shorter and years had more days. Going back even further, about 4.5 billion years ago, when the moon first formed, Earth was spinning much faster. A day might have been only 4 or 5 hours long. The moon was also much closer, only about 15,000 miles away instead of the current 239,000 miles. From Earth's surface, the moon would have appeared enormous in the sky, about 15 times larger than it does now. The tides would have been massive, hundreds of feet high in some places. But, over billions of years, two things happened. Earth's rotation slowed down, and the moon drifted farther away. These two effects are connected. As Earth's rotation slows, Earth loses angular momentum. That angular momentum doesn't disappear. It's transferred to the moon. The moon gains angular momentum, which causes its orbit to expand. The moon is currently drifting away from Earth at about 1.5 inches per year. That's about the same rate your fingernails grow. We know this precisely because the Apollo astronauts left retroreflectors on the moon's surface. Scientists on Earth shine lasers at these retroreflectors and measure how long it takes the light to bounce back. By tracking this distance over decades, we can measure the moon's recession to within a few millimeters. In the future, Earth's rotation will continue to slow, and the moon will continue to drift away. Eventually, billions of years from now, Earth's rotation will slow to the point where one side always faces the moon. This is called tidal locking. At that point, a day on Earth will equal the moon's orbital period. Both will be about 47 current days long. One side of Earth will always see the moon, hanging motionless in the sky. The other side will never see the moon. This is what's already happened with the moon. The moon's rotation has slowed to the point where one side always faces Earth. The moon is tidally locked to Earth. It rotates once per orbit, which is why we always see the same face. The far side of the moon, often incorrectly called the dark side, is never visible from Earth. Not because it's always dark, it receives just as much sunlight as the near side, but because it never faces toward us. The same thing will eventually happen to Earth. One side will always face the moon, but this will take billions of years. The process is slow because Earth is much more massive than the moon. It takes more energy to slow down Earth's rotation than it did to slow down the Moon's. By the time Earth becomes tidally locked to the Moon, other things will have happened. The Sun will have evolved into a red giant and likely swallowed Earth, or at least scorched it beyond recognition. So, Earth's rotation will probably end not because of tidal locking, but because Earth itself will be destroyed or rendered uninhabitable. But for now, Earth is still spinning, still slowing down at 1.7 milliseconds per century, still losing rotational energy to the tides. And the Moon is still drifting away, 1.5 inches per year, carried by the angular momentum stolen from Earth's spin. Second, Earth's orbit around the Sun is slowly changing. The Sun is losing mass through solar wind. Every second, the Sun converts about 4 million tons of mass into energy through fusion. That mass is lost. As the Sun loses mass, its gravitational pull weakens. Earth's orbit gradually spirals outward. The effect is tiny, only about 1.5 centimeters per year. That's less than an inch. But over billions of years, it adds up. Eventually, Earth will be farther from the Sun than it is now. This might actually save Earth from being swallowed when the Sun becomes a red giant. The Sun will expand to about 250 times its current size. Currently, that would reach just past Earth's orbit. But by the time the Sun expands, Earth might have drifted far enough away to avoid being engulfed. It will still be scorched. The oceans will boil away. The atmosphere will be stripped. But the planet might survive as a barren rock orbiting a white dwarf. Third, the Sun's orbit around the galaxy will continue. The Sun will complete many more orbits around the galactic center over billions of years. Each orbit takes about 230 million years. In another 4 billion years, the Sun will have completed about 17 more orbits. But the galaxy itself will change. Stars will continue to form and die. Supernova explosions will scatter heavy elements. New solar systems will form from the debris. And eventually, the Milky Way will collide with Andromeda. When that happens, the Sun's orbit will be disrupted. The merged galaxy will have a different structure. The Sun might end up in a different part of the galaxy. It might even be ejected entirely, flung out into intergalactic space. We don't know. But the collision will change everything. Fourth, the motion of the galaxy relative to the cosmic microwave background will continue. The Milky Way will keep falling toward the Great Attractor. It will keep moving through space at over 1 million miles per hour. Eventually, it will merge with other galaxies in the local group. The Milky Way, Andromeda, and the smaller galaxies will all merge into one giant elliptical galaxy. Astronomers have already given this future galaxy a name: Milkomeda, a combination of Milky Way and Andromeda. Milkomeda will be much larger than either galaxy alone, and it will continue moving through space, pulled by the gravity of distant structures. Fifth, the expansion of the universe will continue, and it's accelerating. This is one of the most profound discoveries in cosmology. For most of the 20th century, scientists assumed the expansion of the universe was slowing down. The reasoning seemed obvious. Gravity should be pulling everything back together. The Big Bang scattered matter outward, but gravity should slow that expansion. The question was whether there was enough matter to stop the expansion entirely and cause a big crunch, a reverse of the Big Bang, where everything collapses back together. or whether the expansion would continue forever, just gradually slowing down. In the late 1990s, two teams of astronomers set out to measure how much the expansion was slowing. They studied Type Ia supernovas, exploding stars that can be seen across billions of light-years. Type Ia supernovas are useful because they all have roughly the same brightness. If you see one that's dimmer, you know it's farther away. By measuring the brightness and the redshift of these supernovas, you can determine both their distance and how fast they're receding. This tells you how the expansion rate has changed over time. Both teams expected to find that the expansion was slowing down. Instead, they found the opposite. The expansion is speeding up. Distant supernovas were dimmer than expected, meaning they were farther away than expected. The universe had expanded more than predicted. The expansion rate was increasing, not decreasing. This was shocking. It contradicted decades of assumptions. Both teams double-checked their results. They looked for errors. They considered alternative explanations. But the data was clear. The expansion of the universe is accelerating. In 2011, the three lead scientists, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics for this discovery. But the discovery raised a huge question. What's causing the acceleration? Gravity pulls things together. It can slow down expansion, but it can't speed it up. Something else must be pushing space apart. Scientists call this something dark energy. The name is a placeholder. It doesn't tell us what dark energy is. It just acknowledges that there's some form of energy causing the acceleration, and we don't know what it is. The simplest explanation is that dark energy is a property of space itself. In Einstein's equations, there's a term called the cosmological constant. Einstein originally added this term to make the universe static, neither expanding nor contracting. He later called it his greatest blunder when Edwin Hubble discovered the universe was expanding. But it turns out the cosmological constant might be real after all. It represents the energy density of empty space itself. Even empty space, with no matter or radiation, has energy. This is called vacuum energy. In quantum field theory, the vacuum isn't really empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence. These fluctuations contribute energy to the vacuum. If the vacuum has energy, and the universe is mostly empty space, then the total amount of vacuum energy increases as the universe expands. More space means more vacuum energy, and this energy pushes space apart. The more the universe expands, the more vacuum energy there is, and the more the expansion accelerates. It's a runaway process. There's one big problem with this explanation. When you calculate the vacuum energy using quantum field theory, you get a number that's about 10 to the power of 120 times larger than what we observe. That's a 1, followed by 120 zeros. It's one of the worst predictions in the history of physics. Nobody knows why the calculated value is so different from the observed value. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. Despite this problem, the simplest model that fits the data is a cosmological constant with a very small positive value. About 68% of the universe's total energy comes from dark energy. About 27% comes from dark matter, and only about 5% comes from ordinary matter, the stuff we can see. Atoms, stars, planets, gas, dust, everything visible makes up only 5% of the universe. The rest is dark, and we don't know what it is. Dark energy doesn't clump together like matter. It's spread uniformly through space. Its density doesn't change as the universe expands. That's why it becomes dominant over time. As the universe expands, matter becomes more dilute. Galaxies get farther apart. The average density of matter decreases, but dark energy's density stays constant. So, as the universe gets bigger, dark energy becomes a larger fraction of the total. Eventually, dark energy dominates completely. The acceleration has been going on for about 5 billion years. Before that, the universe's expansion was decelerating due to gravity. But as the universe expanded, matter became more dilute. Gravity's influence weakened. Dark energy's influence remained constant, or possibly even increased. Eventually, dark energy took over and the expansion started accelerating. In the far future, the acceleration will continue. Distant galaxies will be pushed beyond our cosmic horizon. The observable universe will shrink. Not because the universe is getting smaller, but because light from distant galaxies will never reach us. The expansion is carrying them away faster than light can travel toward us. Eventually, in trillions of years, the only galaxies visible will be those gravitationally bound to our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies. Everything else will have been carried away by the expansion of space. An observer in that far future will look up at the night sky and see only their own galaxy. Maybe a few nearby galaxies, if any, remain separate. They won't see any other galaxies. They won't see the cosmic microwave background. It will have been redshifted into invisibility, its wavelength stretched to infinity by the expansion. They'll have no evidence that the universe is expanding. They'll think their galaxy is the entire universe. They'll think they're alone. They'll have no way to discover the Big Bang, no way to measure the age of the universe. All the evidence will have faded away. We're living in a special time. A time when the universe is old enough for stars and galaxies to have formed, and for intelligent life to evolve, but young enough that we can still see the evidence of the Big Bang. We can still see distant galaxies. We can still measure the expansion. We can still detect the cosmic microwave background. In the far future, that won't be possible. The evidence will have disappeared. Any civilizations that arise in the distant future will be cut off from the knowledge we have today, unless we leave a message for them somehow. This makes our era unique, not just in human history, but in cosmic history. We're in a window of time when the universe's deepest secrets are still visible. So, all of this motion, all these incredible speeds, they're part of a universe that's constantly changing. Earth is moving. The sun is moving. The galaxy is moving. And the universe itself is expanding. Nothing is stationary. Nothing is permanent. Everything is in motion, and everything is changing. So, what have we learned tonight? We've learned that you're moving through space at over 1 million miles per hour. We've learned that this motion is layered. Earth's rotation, Earth's orbit, the sun's orbit, the galaxy's motion, the expansion of space, all happening simultaneously. We've learned that you can't feel this motion because it's smooth and constant and everything around you is moving with you. We've learned that motion is relative, that there's no absolute speed, only speed relative to something else. We've learned that this motion affects how we see the universe, how we navigate through space, and even how we measure time. And we've learned that this motion will continue, changing over billions of years as the universe evolves. But here's the most important thing. None of this motion matters to your daily life. You're sitting still relative to your surroundings. And that's the only motion that matters for your immediate experience. The fact that you're hurtling through space at incredible speeds doesn't change anything about how you live your life. You're still you. You're still here. You're still experiencing the world the same way you always have. But knowing about this motion, understanding it, that changes something else. It changes how you see yourself in the context of the universe. It reminds you that you're part of something vast and dynamic and constantly moving. You're not separate from the universe. You're part of it. You're riding along on a planet that's riding along in a solar system, that's riding along in a galaxy, that's moving through an expanding universe. You're connected to everything. Every atom in your body was forged in the heart of a star that lived and died billions of years ago. Those atoms have been moving through space ever since, orbiting the galaxy, collapsing into new stars, being blown apart in supernova explosions, eventually finding their way to Earth and becoming part of you. You're made of stardust, and you're moving through space at the same incredible speeds as those stars. You're not just on Earth. You're on a journey that started billions of years ago and will continue long after you're gone. A journey through space and time. And even though you can't feel the motion, even though it seems like you're sitting still, you're part of this vast cosmic dance. And that's something worth thinking about. So, the next time you're sitting quietly, maybe at night looking up at the stars, remember this. You're not still. You're moving. Faster than any car, any plane, any rocket. You're moving through space at over 1 million miles per hour. And you're doing it right now. Every second. Every moment. You're on the ride of a lifetime. And you didn't even have to buy a ticket. Thank you for joining me on this exploration of motion. If you found this journey through space fascinating, please consider liking this video and subscribing to the channel. It helps me continue making these deep dives into the cosmos. And remember, you're not sitting still. You're moving through space at incredible speeds. You just can't feel it. And that's one of the most beautiful mysteries of the universe. Sleep well tonight, knowing that you're part of something vast and dynamic. You're traveling through the cosmos at speeds that would make the fastest rocket look slow. And tomorrow, when you wake up, you'll have traveled millions of miles through space. All while you were dreaming. The universe is in motion. And so are you. Good night.